I would like to kick it off and introduce our first speaker, Chad Sanderson, Head of Product and Data Platform at Convoy. I think to many of you, Chad is known for his hot takes and strong opinions about data contracts, something which is currently, I think, is a really active topic that is discussed in the data community, rightly so, I think. So Chad, please welcome to the stage, and really excited to hear about data contracts.
Excellent. Thank you, Gleb. I'm going to go ahead and share my screen here.
Oh yes, something I forgot to, well, you set up, Chad, something I forgot to tell everyone. Yes, the event is recorded, so we will absolutely share the recording and all the talks afterward. So you can watch it later, share with your peers.
Okay, well, I'm ready to go. Well, hi everybody. Hope everyone's having a good morning, or if you're not on the West Coast, then whatever time zone you happen to be in, or time of day. My name is Chad Sanderson, and I am the head of data platform on the product side at a company called Convoy, which is a digital freight technology startup. And data quality is extremely important to Convoy, and that's because data is extremely important to Convoy. Essentially, our entire business is built on the data we're getting about our customers, on shippers and carriers, and we leverage machine learning, all types of automation, and business intelligence in pretty much every single decision that we make. And that means that the quality of those decisions needs to be high, and it generates like real ROI for the company. And we ran into some problems with the quality of our data and the trustworthiness of our decisions. So pre-data contracts, the way things looked at Convoy was we were primarily capturing data from two main locations. In our first-party data is we were either using a tool like Mixpanel to capture events from our front end, not so much on the back end, piping those over to their SaaS platform, and then importing all of that data via Fivetran to the cloud data warehouse. We use Snowflake for that. And then on the other side, we were following that same process for our data in S3. We were essentially pointing a Fivetran connector at Postgres tables, importing all that data into Snowflake again. And so what essentially was happening is we had these big sort of data dumps that were arriving in Snowflake, which some teams then needed to understand, figure out, sort through. And it really became a big mess, especially when we started moving to a more centralized system where each product team was responsible for their own business logic. And so what that resulted in was we ended up using a lot of tools, things like Amundsen, dbt, Airflow, and like fundamentally the quality of our data, the data itself that was coming over the wire from our production systems was not high quality. It wasn't designed for analytics or machine learning. And the producers of the who were generating the data really had no responsibility to ensure that it remained of high quality. So in the old world, we had a bunch of problems where, because we had these non-consensual APIs, we were just taking mass exporting batches from production tables that no software engineer really agreed to. Then the data producers never took accountability of the data quality itself. The software engineers were not aware of how their data was even being used downstream at all. And so because of this mess that was arriving in Snowflake, it was really hard to understand what that data actually meant and from how was it being defined in production. We lacked a lot of documentation. A lot of the data modeling was not done in advance, which made things really hard. We didn't have a real source of truth. And there was an enormous cost to validate that the data we were bringing in was actually high quality. For a lot of our machine learning models, we ended up filtering out somewhere between 10 and 50% of the data, which meant that we weren't actually training our machine learning models on reality at that point. And so inevitably, something that should have really taken hours or minutes to understand inevitably ended up taking weeks. And so the core stance that we had here was that that just shouldn't happen. Science and analytics were first-class consumers of our production applications, and we needed to treat them that way. Our engineering team needed to treat data as part of the product, and that meant providing data over the line as an API. And the vehicle that we wanted to use to facilitate this transition was the data contract. So a data contract is an agreement between a producer and consumer on the data that's generated for some production grade use case. And that refers specifically to its schema, values, SLAs, and semantics. Why are data contracts sort of the right tool for the right job? Oh, the first thing is they define clear ownership of the upstream data. It facilitates a conversation between the producer of the data and the consumer of the data on like what's expected, why is it expected, what use case does it serve, and what is the value. And it also provides a single surface for semantic definition. Each contract essentially is mapping to a single semantic object, whether it's an entity or an event, and that makes it really easy to do data discovery. And most importantly, it serves as a surface for collaboration between two teams that generally do not talk to each other. So the high-level way of thinking about contracts is really a very simple contract is just the schema itself. So ensuring that the schema doesn't change in some unexpected way, that if you have a field that needs to be null, that it stays null. But you can very quickly dial up the complexity of the contract over time, focusing on, are some set of values always remaining the same? Is the business logic and the semantics of some particular column consistent? Is the latency, is the SLA as expected, and so on and so forth. So the maturity of the contracts really depends on where you are as an organization, but I find starting at schemas is the right approach. And there is a technological implementation here. In fact, we just published an article yesterday on how to implement data contracts from an engineering perspective. At a very high level, there's a few different pieces. You basically have a development workflow. We focus on protobuf as our contract definition surface. You define the schema there. After you define the schema, you then incorporate it into the CI, the checks, the integration tests into the CI/CD workflow of the software engineer. And so if those tests fail, if you're making a backwards incompatible change, then we can actually break the build. And then you have the ability to publish those schemas through the Kafka schema registry, push it via Kafka through an entity topic, as we call it, into the warehouse. And that's generally the way that it's managed. So there's a lot of complexity into this system, but I find it's an awesome place to get started, is referring back to that article. And today at Convoy, we have roughly 300, I think maybe 320 to 350 contracts that are actually in production that are, and thousands of changes are made to those contracts every month. There's a lot of collaboration around them as well. So big takeaways for contracts is that they're really critical for production grade data pipelines. So when you have some use case that requires quality, the generating the contract is actually an act of collaboration between the producer and the consumer. Being able to enforce the contract is critical. We do so in the CI/CD pipeline by breaking the build if the contract is not being met. Didn't talk about this too much, but abstractions just make it a real easy implementation and nicer for the software engineers. And then the goal is to eventually focus on the definition of the semantics in production systems, not just accepting sort of what we're getting from these more operational use cases. So there is a guide, an implementation guide. Here's the link. I have a Substack just called Data Products. But that's it. That's my talk. Thank you.
Thanks, Chad. Well, my takeaway is data contracts are both quite simple as an idea, but also could be a really complex of an implementation.
Yep, that's exactly right. There's a high ceiling.
Yeah, and I'm really excited to see if there are any possible frameworks or implementations that would make it really attainable to majority of data teams who would, let's say, not be running like full scale streaming infrastructure with Kafka and Flink. So I'm really curious about how that could map to more of a modern data stack. Like, if you're using Fivetran, let's say, to extract data from your transactional systems into analytics, and then you're using something like, Rudderstack or Segment for events, is there a place for data contracts? Or is it something that you just need to really own internally and build like a full scale engineering system around it?
Yeah, I think that something like that probably will emerge. The only thing that I will say, I love the idea of using sort of the modern data stack as sort of the vehicle to implement contracts. The important thing, though, is, and we say this in the article, is that it's really not a contract unless it has the ability to be enforced. If it's just a consumer saying, "Hey, this is the data that I want and that I expect," it's not a contract. It's more of like a handshake agreement. And so, being in that CI/CD pathway is like super, super critical. And as long as you're accomplishing that, I think that it has the potential to work.
Awesome. Well, I have more questions, but I'll leave them for the final discussion because I would love to hear thoughts of our other guests today as well. Thank you so much, Chad. I would like to introduce David Jaitalakar from Metaplane. David is head of data at Metaplane, another company who is focusing on data quality. David is very active in the space, and I'm following a lot of his takes on modern data stack tools and beyond. So really excited to have you, David. Please take it away.
Thanks for having me, Herb. Let me just share my screen. Great. Yeah, so my name's David. I'm head of data at Metaplane. So there's some details below if you want to follow me on Twitter or contact me in other ways. My talk today is on observability versus quality in data. So some context, I think data is becoming a product. I think we're well aware of that, and pretty much everyone on this call will be. It's long gone are the days where data is just something that goes into BI and then it's some report that is used or not used, right? The data that we're producing today is being operationalized, is being used for machine learning, product experience, in-session actions, and business intelligence, which is becoming more important than it used to be. But more data, more problems. So things inevitably break. And what's one of the real problems with this is data is something that needs trust from an organization. So if the trust gets broken because stakeholders see broken data or they make the wrong decision based on broken data, the impact of data in an organization gets reduced, which is the exact opposite of what we want as a community. So what's the problem? Data analytics engineers are fixing things after the fact, and this is like very related to like what Chad spoke about. Data needs to be a first-class system of application development in the CI/CD flow, and what we should be thinking about is trying to move, further to the left in the DAG to improve quality. And so there are quality and observability approaches that we can take to prevent data going into the red zone. So this is a quote from Kevin, who's our CEO. Data is more fragile than software. So in software, there is a line which goes, treat software like cattle, not like pets. In data, it's more like thoroughbred racehorses because lineage matters. And I think one of the things is with data, when it's broken, you can't just fix it and it comes back up again. You can lose data, data is corrupted forever, and sometimes it's completely irreversible when it's broken. So data observability. So data observability, it's a term that I think a lot of experienced data practitioners kind of scratch their head about. What is data observability? So I think it's really interesting within the context of testing, where testing is around asserting something, typically about like a Boolean outcome. This is true or this is false. My primary key is unique or it's got duplicates. This column has nulls or it doesn't, right? That's what testing is great at. What observability does is it monitors trends of scalar values. So things like, let's say, for example, you have a table where there's a foreign key. The foreign key can be null, and let's say it's null 8 to 10% of the time. There is going to be some tolerance, a statistical significance, where if you've breached that, it's not. It's probably an anomaly, and it could be a data quality issue. So that's exactly what data observability tools do. We track things like freshness, so how recently has your data been updated, and is that in sync with what you need or what you'd expect, and what has happened in the past, more specifically. And we do things like schema change detection, cardinality. So let's say you've got a field which is an enum, like marketing channel, for example, might have 10 values, but it could, if you lose one or you get a new one, that's something you want to know about. So there's a few different things observability tools can help in terms of quality. So quality assurance is, as I said before, it's asserting what good looks like, and it's usually a Boolean outcome. So things like DBT tests, which you're probably quite familiar with, but there's actually not that many tools on the market to help you with this. But it's something that we do need to invest in as a community. So in software engineering, test suites are a huge part of the cost of building. I've seen projects where a software engineer has changed like one line of code and had to write 40 lines of tests, right? So it's something that we need to actually invest in as a profession, because it's just unavoidable if we want quality. There is a balance between coverage and complexity as well. We can't write a test for everything. And I think that's where observability is really helpful as well, because often when you're trying to write too many tests, it's because you're trying to estimate that confidence interval, and you're trying to set upper and lower bounds, and that's actually where tests don't do well. So some specific examples of quality assurance. So for example, and this is, again, goes back to data contracts a bit, managing your tracking workflow to ensure that complete and correct data is captured. So you can test it against, say, like a JSON schema or a data dictionary to make sure that it is the way you want. It's complete in terms of fields, got the right data types, etc. But then there's also things like data diff, where you can test different data sets, well, the same data set from different environments to see if there's a possible quality issue. And you can do that on like a row by row basis or in other ways. So what's needed? I think both. I don't know a CTO who hasn't got a New Relic, who hasn't got Datadog or one of those tools, incident.io. They all have one of those. They also all have a test suite. It's not one or the other. And we've had that question from many people. Oh, shouldn't I just use tests? No, you should use tests and observability. And there's also increasingly things that can be inserted into the CI workflow. So you've got things like data diff, which can check inside the CI workflow for problems between what you've proposed in your code and what already exists in production. And then things which can also tell you about downstream dependencies, whether like BI tools or different DBT models. And that's my talk. Thank you.
Thank you, David. Super supportive of the idea that there is no single answer to data quality, just because it's an extremely complex problem, just like in software quality. And you do have to pretty much approach this from a combination of kind of pre-production testing, post-production monitoring, and I think while all the vendors are tackling this problem from different angles, a lot of the times we kind of make it seem that, well, we should go with one solution in particular because we have the answer. Well, in fact, just like in software, you need different approaches because you catch different types of errors. And some of these errors are just like related to process and culture that maybe you don't even need a tool. You just need to improve how your organization works. So really exciting highlight of the problem.
Yeah, thanks for that. I could definitely see that with data, there's this additional complexity of the state of the data in different environments, which is a problem in software engineering, but it's not as big of a problem as in data.
Yeah, totally. Awesome. So I'd like us to move forward with our next talk and invite Michael Lowe, data engineer at Virgin Media O2. Michael, I came across Michael and Richard will join us for the panel work on building a data platform for Virgin Media. And what really impressed me in their article is that they built a really self-sufficient data platform using pretty much just the Google Cloud infrastructure. And I think what's interesting here is that typically most data platforms are a mess, and it's a mess because we kind of look for different tools that each do a best job at something. And then a lot of times the compatibility of those tools and the overall user experience can be really bad just because of how non-cohesive the user experience is and potentially the breakage between the different integration points. And so it's been really exciting to see how for such a large company, they were able to build a data platform that accomplished a lot of the needs using a single, more of a cohesive experience. So Michael, please take it away.
Right. Okay. Let me share my screen. Yes. So hi everyone. I'm Michael, a data engineer from Virgin Media O2, Advanced Analytics and Data Science team. I'm here today to talk about a standardized and scalable ways for sharing data in real time. So a bit of background, Virgin Media and O2 were initially like two separate entities, and actually we merged last year to become Virgin Media O2. And our vision is actually to become a digital first company in the UK, in the telecommunication industry, and to use like data to elevate our customers' experience. We want to centralize all our data in the cloud and hopefully make the right data accessible to relevant stakeholders for them to actually build platforms to serve the customers in more intelligent ways. So as you can see in this slide, on one end, we have incoming data from third-party data providers, as well as in-house microservices. While on the right side, you can see we have analytical and operational consumers that want to utilize these data. Thus, we actually built a Vortex engine as a data ingestion platform with some criteria that we set. So number one, it has to be able to rapidly ingest API data. Number two, it must be able to handle real-time events as well as batch ingestions. Number three, it has to be a generic service of high scalability so that it can serve different target destinations. And lastly, we do not want to create like endless amount of cloud infrastructures on GCP to service all of these data. So this is a simplified architecture diagram for Vortex engine. And it only contains, for this diagram, it contains the necessary GCP services to get you or anyone started. So it can be broken down into three main aspects. On the left is the ingestion methods. In the middle, the message queue. And the last part is data processing for the analytical pipeline side of things. So the data actually are ingested either through the Cloud Run or Cloud Composer. And the payload from these services are packaged and published to a message queue. before sending to either the analytical or actually both analytical and operational pipelines. For the analytical pipeline, we have a data processing component that actually only does light transformation before determining and pushing the message to the its destination tables in our BigQuery data lake. So in the subsequent slides, I will actually cover in more detail of each individual component. So as for ingestion, those data sources that require API request ingestion methods are orchestrated by Cloud Composer, which is actually a fully managed workflow orchestration service built on top of Apache Airflow. And we manage this direct acyclic graphs via a framework built on top of Airflow to actually fetch and publish this payload to the downstream PubSub topic. And for us, this published messages actually follows a generic JSON message structure that is predefined by us. Next is the real-time event-based ingestions. So all these messages are actually sent to a single Cloud Run API service, which publish the same PubSub topic as well. So similarly, this service will also enforce the same consistent generic message structure. So now that we get all of this message from upstream into this one PubSub topic, we actually utilize like a one-to-many publisher to subscriber relationship to distribute all these messages to different subscriptions. And all these subscriptions can actually utilize or use to filter messages based on the topic using a given attribute, so that different operational consumers downstream are able to retrieve the data relevant just for them. At the same time, for us, these messages will be processed by the analytical pipeline to store in the BigQuery data lake. So as for the analytical pipeline portion, we chose Cloud Data Flow for data processing, and so that it's able to handle large amount of streaming messages by auto-scaling the number of workers. And we actually chose to deploy our own custom data flow pipeline, as the one that provided by Google can only handle like a single source to a single BigQuery table output. So on the picture on the left, you can see like the data flow pipeline takes in two inputs. One is the main input, and secondly is a side input. So the main input actually takes in the messages from the upstream PubSub services, and the side input reads this slow changing lookup table triggered by this metadata management service. So what does this metadata management service do? It actually creates three unique things. One is the universally unique identifier. It also creates BigQuery target tables, as well as this special table containing the metadata of all of these target tables. So if there's any changes or creations within this metadata management service, it actually triggers the updates of the lookup table. So additionally, the identifier created by this service must be added as an attribute in the PubSub message before publishing it to the service. So how do we determine where these messages will land or which table it lands into? So the identifier that is created will be used to look up for the BigQuery table ID in the side input, and eventually writes the message to the respective table. So another point is if there's any validation within the data flow job or tables that are not valid, the message will actually be sent to this additional date letter queue PubSub topic, which we can actually reprocess all this message again. So this slide shows some images that gives a brief overview about the capability of Vortex Engine manage managing the analytical pipeline. So on the left side, the images, we can see we did a simple load test of about 4,000 event messages sent to the Cloud Run service over a 2-minute period with a single Dataflow worker. And we can see that we are able to activate these messages with a 50th percentile about in 7 seconds, seen in the pub/sub act latency graph. Yeah. So on the right side, you can see is a representation of the past 24-hour timeline on an earlier stage of our UAT environment, similarly with one Dataflow worker. And the difference in spikes in the pub/sub latency actually represents the batch ingestion scheduled by the Cloud Composer with ongoing event-based message, where the larger spikes or amplitudes are means there are more messages and records from both the batch and ongoing events. Yeah. So on average, that would take about 0.7 seconds to act each individual message. In the bottom graph, it actually shows the different number of BigQuery tables indicated by different colors that the Dataflow job actually output to throughout the entire day. Of course, this latency performance can be actually improved easily by increasing the number of Dataflow workers, but this of course comes with more costs. But another way is of course having more effective or efficient Dataflow pipeline stages. So with Vortex engine design, the parallel running operational pipelines with these analytical pipelines, it will actually not affect these latencies by the operational pipelines, which actually are limited by downstream consumer systems. So lastly, we actually envision Vortex engine to be a software as a service platform that hopefully empowers all our users like data analysts or scientists with the speed, flexibility, and ease to integrate their end-to-end data pipeline to bring more value to our customers. Yeah, so thanks for listening. If there are actually more details about Vortex engine in the article that I wrote in the link below. Else you can connect with me on LinkedIn and we can of course discuss more about this. Thanks.
Awesome. Thanks, Michael. I'm curious, how many engineers, how big of a team worked on the Vortex engine?
Sorry, yeah. Could you repeat the question again?
Oh, how many people worked on putting together the Vortex engine? How big of a team?
Yeah, initially it was a small team of about 3 of us. Yeah, so we worked on a few different components, like of course the Cloud Composer as well as the event-based Cloud Run service, as well as the last person working on the Dataflow portion. But I think we are scaling larger, so right now we have about 4 to 5 people managing it. But yeah, we are trying to hopefully within a couple of months' time, it will be a self-service kind of platform for the entire wider organization.
And how long ago did you start working on it?
So we took about 6 months or less to build end-to-end. Yeah, so I think it's quite an achievement for small team that focus on this. Yeah.
Yeah, I think given the scope of what it does, building it in 6 months with 3 people is very impressive. So kudos to the team. And I think it also highlights what can be achieved if you use more like pluggable components in the cloud platform with all the services versus, in my experience, dealing with more kind of like self-hosted open source solutions. For example, the alternative to the architecture you presented could be something like running, Kafka and other open source solutions and hosting them. I'm pretty sure that would take way longer than what you've done. So I think it also highlights how fast things can be actually implemented, even if they are actually very complex in nature. So awesome. Thank you for sharing.
Yeah, thank you.
Cool. So in general, we are mixing the topics of data engineering and how to build data pipelines and data platforms with the topics around how to ensure that data is of high quality. So our next talk by Ismail Adu, who is a data engineer at Doctolib, is actually focusing on ensuring the data quality once your data platform is in place. So Ismail, please, welcome to the stage.
Thank you.
Take it away.
Thank you, Gleb. I will just share my screen. Okay. So do you see my screen? I think you see. So thank you. Hello, everyone. I am really happy to be with you today to share my feedback about testing process concerning our data warehouse. And we will talk about how we implement CI2, especially for Redshift. So to present myself a little bit, my name is Mail Addo. I have 4 years experience in data engineering and cloud infrastructure. And I began to write some articles in my Medium account. And today I will be talking about my last article. I dropped a link here for more details for the ones who want to see. So I work in Doctolib. It's a French company based in Europe since 2013. And for those who don't know Doctolib, our product is mostly known as a booking app for healthcare services and also for teleconsultation services. But this is just the only visible part of the iceberg, because we are developing many other tools that offers a new work experience for doctors or healthcare practitioners in general, and enhance the medical journey of patients. So about our data team, we are almost 40 Doctolibers now, working on many projects on AWS. But today I will focus on our subject, which is the data warehouse, where many of us are very active, because we push an average of 25 commits per day, and we try to keep the time to production less than 1 day. If you code it the morning, you will find it the evening in production. So also we have the objective to keep SLA under 8 a.m. And this is so challenging for us because a high coding velocity is also a high risk of pushing code errors. So we are using Redshift, as you know. It is a relational database and a strongly typed one. Then every structure change should be explicitly defined in a migration script in order to avoid a failure in production. And also in our data warehouse, we are using many data marts that are dependent on each other in the same database, which makes them all vulnerable to failure at any point during the workflow. So we are not safe from code mistakes, from data source unpredictable changes that could come from outside, and what I call database conflicts. For example, when we have 2 commits, one will rename a column and the other is still using the old name in a new SQL query. We are not aware of this conflict only on production if we don't do a system that will prevent from that. So if you have a pre-prod environment and an access to real data, this step will be easy to set up, and even it could be a must-have to test issues that are coming from data especially. So we automatically deploy and test a release candidate to pre-production during the afternoon. Once the tests are green, we are able to push to production. As we are using real data here, we're able to detect problems related to the data, like structural changes in data sources, overflows, or maybe queries that is taking too long, for example, due to a bad join. But when it comes to code mistakes and database conflicts, it detects them, but it is far from being the perfect solution, because when everything is okay, it's okay. But when we should repair the problems that are only coming from code base, and that's happened more frequently, tests in pre-production with real data are heavy. It takes 3 hours to complete. So we have to fix the pre-production locally, manually, and push a fixed version later to the prod in the same day, because we want to push in the same day. And this requires a lot of manual work for the duty. So we are a big team, and this could happen frequently, and one bad commit is enough to ruin the pre-production. So to have a better testing for problems related to the code base, which are the most frequent problems, This slide won't surprise you. We will implement a CI pipeline to detect issues coming from the code base only. So like code mistakes and database conflicts. So we moved from a detection approach in the pre-production to a prevention approach. So before merging to the main branch, a CI process should test all the workflows to validate whether the PR should be merged or not. So the good news here is that we will do the same as pre-production, all the tests, but without a need of data. So we can save time to have quicker tests. Therefore, we'll be able to run multiple tests in the same time with short durations. So what we need to do is create isolated environment for both Airflow and Redshift. So let's begin with Redshift. So we dedicated a new cluster with the minimal configuration possible, as we don't need data, we don't need performance. So you can imagine that for each PR, a CI will be triggered and it will create a temporary database that is very similar to production, but without data. So the best way to do that is to use DDL queries in the link here. In our case, we cloned the entire database. I can say thousands of assets in only 15 seconds. So we have our database for our PR tests ready. And when we try to test with Airflow environment, it took us 1 hour to complete, and this is much longer than expected. So we noticed that we have more waiting time between tasks comparing to the execution duration in Redshift. And this is due to the slowness of the scheduler. So the scheduler system rely on the metadata database a lot to orchestrate the tasks, and this costs very much in terms of performances. So we don't really need all the features of a scheduler. We only need to orchestrate. So what we did is that we implemented a homemade orchestrator based on Airflow library to make it aware of task dependencies according to the tags, and also to execute the operators that are coded in Airflow inside the script. So we moved from 1 hour of execution to only 5 to 7 minutes to execute all the CI pipeline, including the database creation and destruction, and also the migration that we do before beginning the scripts. So to summarize, we had 2 types of problems, and those that are caused by the data coming from outside. It couldn't be avoided completely, actually, for the simple reason that it could happen during the night or during holidays. It's not really related to our coding. But all the problems that are related to the team internally, the CI pipeline do the job perfectly. So to finish my speech on this word, we still push to prod every day, but we still have green lights everywhere. Thank you for your attention.
Awesome. Thank you so much, Ismail. Emil, this is great. And I think in general, the power of CI and proactive testing is vastly underrated for data. I think there's a lot of discussions of how do we detect issues in kind of the post-prod environment, but also to the point that David raised earlier, there's also a lot you can do before. And it's really great to see what you were able to do with Airflow, given how, I wouldn't say bad, but well, it's actually pretty bad at testing because it doesn't have any sort of like dev environment. Everything is essentially prod. So really exciting to see how you were able to actually make it such that you can test for all the kind of human introduced errors before production. That's really, really neat.
Yeah.
Cool. Our last but not least lightning talk is from Max Regenthaler, who is CEO and co-founder of Nixla. So I think in data community, whenever we think about forecasting or any kind of anomaly detection in time series data, we all know a very popular library called Prophet. And that library existed for years, and it has its own pros and cons. And I was really excited about learning about Nixla and invited Max to present, because I think in general, a lot of the things that we do, especially around data quality or forecasting or identifying any kind of anomalies in data, they are in many ways distillable to time series forecasting. And it's great to see that there is finally a lot of great innovation happening in that particular area, because it does solve lots of problems, both for data quality and just in general for business. So Max, super excited to learn more, and please take it away.
Thank you very much. And yep, we also believe that time series data is quite ubiquitous and that is very important in different domains. Classically, it was used for demand forecasting, supply chain optimization, electricity problems, but we are seeing a lot of growth in the observability and data quality space to detect anomalies, to forecast the future loads, and do infrastructure provisioning. So we are very excited to be here and talk a little bit about time series data. So formally speaking, the forecasting problem could be defined as follows, but many of us who are in the field really feel more like this in our day-to-day. And today, in this lightning talk, I'm going to be speaking about how Nixla came to be, and hopefully that reflection on our story can serve as a reflection on the field, which, as we understand it, is a reflection that struggles between constant tensions between different opposites. And one philosopher and three econometricians walk into a bar, and what happens is Nixla came to be. There is not punchline. There's no really joke here. This is really how it happened. And coming back to philosophy, I think there's, if I remember it correctly, this idea of Hegel that history could be described as progressive evolution, where you have like different opposites that somehow, after like a dialectic movement, come to a synthesis, and that's more or less how we see the story of Nixla. The first tension that we encountered when we started doing time series analysis and time series forecasting back in that day, we knew how to write R. We were students and we were trying to do some demand forecasting for a big retailer in Mexico, where we're from. And it was amazing to see how many libraries were available for statistics and econometric models. But then we started to learn about Python and how great it was for data related tasks and for more scalable pipelines, and also a lot better for deploying into production. But in Python, there was a big missing link, namely a solid and robust alternative for statistical models. So we decided to create Stats Forecast, which was the first library that we started working on. And with Stats Forecast, what we are trying to do is bridge the gap between R and Python, so the data community in Python can foster the benefits of these amazing classical methods. We ported a lot of what was done by a very famous practitioner called Rob Heinemann, and created the fastest version of ARIMA out there, the fastest version of ETS, also the most robust one. And at that point, we wanted to compare ourselves with the leading library, which was Prophet, with many users. And after doing some experiments, we were amazed to see that a very classical model, ARIMA, was a lot faster, also almost 40 times faster than Prophet, and also more accurate, like 70% more accurate, which is important, because if you are running, for example, this experiment, which is a very famous benchmark data set in the field, you would not only gain 70% accuracy with Prophet, with ARIMA instead of Prophet, but you would only pay $10 using the instance that you see there, instead of paying almost $300. So it's not only faster and more efficient, it's also at the end of the day a lot cheaper. And we saw great results from the community. They were quite engaged and published some interesting stuff. And that's when we realized we were into something, and that we were tapping into an actual need of the data community in Python. But then, after trying to resolve the first contradiction between R and Python and creating Stats Forecast, a new tension arose, namely the classic tension between machine learning, data science, and classic statistics, or the classic tension between interpretability versus accuracy. And there's even like rap battle videos here. You can go and check it out. And in the field, the second tension is expressed as the tension between the classical autoregressive models used by statisticians, econometricians, and financial practitioners, and the newer, maybe more accurate, but a lot less explainable, newer deep learning models. And with what we try to do there is a part of the research that we have been publishing, namely contribute to the field with models that are not only very accurate and leverage the advantages of deep learning in terms of scalability, simplicity of pipelines, and also accuracy, but are also in the line of decomposing the signal into different interpretable blocks. And that's what we did with this expansion of a very classical model called the NBITS. And that's also what we did with the NHITS, which offers interpretable forecasting tools and decomposition of signals for long horizon forecasting. But we wanted to make this available for the community. So we created this other library. Everything is open source. Everything can be used and tested by different data practitioners. We created this other library called neural forecasting, where we included the models that we developed, but also other probabilistic forecasting methods, so the community can use them. We have seen some interesting adoption from people doing anomaly detection at the observability space. So if you are interested in trying this out for your use case or your platform, we're happy to help you and speak with you. And at the end, as I was mentioning at the beginning, an interesting spiral started to emerge. So from the different opposites, some new things came to be. And that's how the Nixlaverse or the different sets of libraries came to existence. I talked today about neural forecasting or deep learning and forecasting. I talk about stats forecast, but we have also been working in new libraries that solve different problems, like the hierarchical forecasting one and the machine learning forecasting platform. So if you like the talk and you want to see what we're doing, please support us at github.com/Nixla. And we promise we won't talk anymore about philosophy. Thank you.
Awesome. Thanks so much, Max. I think what's interesting is that in data, there's like two trends. One trend is obviously there's so much excitement, so much infrastructure built around deep learning. And I think from the outsider, it may seem like deep learning is the answer to absolutely everything. But then when you talk to actually, practitioners who are super deeply involved in certain forecasting problems, like for example, like you, Max, then we see the sort of comeback to time-proven methods that were invented years ago and used by econometricians and statisticians for years. And I think I also came across an article recently that said that some of the better, the most, I think, like generally applicable and high-performing model for tabular data is actually a decision tree for variations of decision tree versus actually deep learning. So I think it's kind of the contrarian trend to all the deep learning excitement. Cool. So that's it with our lightning talks. I would like to invite all our speakers to join the panel. So you don't forget to unmute yourself if you're speaking. So I have a few follow-up questions related to the lightning talks that I think are interesting to double down on. So one is data contracts. I think the way I understand the value of data contracts is kind of twofold. One is obviously we want to get reliable data, and then the how of data contract is basically if you have a formally defined contract which basically describes what kind of data, by whom, when, in what format is produced, then whenever this changes, you can have reliable change management and avoid surprises. And second, you can do more like automated discovery and understanding of those data assets by other people. I think what's also like not obvious, maybe obvious even, is that from the slide that Chad showed, it's a really, really complex system. and it seems to be focusing on the kind of the streaming part, the generation of data by services, basically emitting events in lots of different events at high velocity, but potentially transactional exports. But I'm curious how we think about application of data contracts for more one, like conventional data platforms. So if you're not running as complex architecture, how that applies to you, and two, how does it apply to non-streaming world? So should we supposed to have data contracts for data which is in Snowflake, like tables that we build, right? So really curious to hear thoughts from you, Daniel, since you worked on this problem, but also from our data practitioners guests today.
Yeah, I can definitely speak a little bit to kind of what we've done at Convoy. So I think you kind of hit it on the nail on the head, which is that we kind of started off with the data contract journey of we wanted to make data more reliable. And before we took advantage of any kind of streaming platform, our goal first and foremost was to get engineers on the production side and the data engineers and data science folks on the data side to just kind of come together, figure out what our production use cases were, and then kind of agree to what is going to be produced and how it's going to be produced. All of the additional streaming complexity stuff came either we were taking advantage of existing infrastructure at Convoy that we were using, or we were building things to solve specific problems that we ran into at Convoy. So for example, we wanted to basically be able to take advantage of an abstraction layer where even if engineers on the production side wanted to change the underlying database, we still wanted to give them a surface to be able to emit events or produce events in a standard kind of shape that they had been agreed to. And we had this streaming infrastructure kind of set up already, so we took advantage of that. So yeah, but that being said, we kind of started first and foremost with the problem is let's agree to a shape and detect changes before they are actually pushed. And so that part doesn't necessarily need to take advantage of the streaming aspect. It's kind of the initial gatekeeping of kind of how you get reliable data. Yeah.
I think on the point of non-streaming data, I think, and I've written about this, but I think a lot of data that looks batchy or is not actually batch data. Like let's say, for example, the typical example of like an OLTP database, which you extract data from Fivetran as like a batch sync. Really what's going on that OLTP database to generate the changes in the data are events are happening which are triggering transactions on that database. And that's why you're seeing like the proliferation of CDC as a way of moving that data, and therefore having data contracts on that stream. So that's one element I'd say about the batch part. Sorry, what was the first part of the question? I've forgotten it.
I think the other part of the question is, so how does the concept of contracts, which is basically codified formal definitions of data assets produced throughout the pipeline, applies to the more classic modern data stack world, right? So if we're doing something like Fivetran router stack, Airbyte data extraction, then using something like dbt on the cloud warehouse. Like personally, it's hard for me to see how that fits and how that's implemented unless all those vendors start talking to each other in something different than just SQL and kind of throwing tables around.
Yeah.
Is there a world like that, do we need this world? Do we need these kind of contracts in this modern data stack environment?
I think I think maybe this is one where maybe, like if you think about a DBT model, which is a table, right? I guess that is a true batch process, right? You've just run a query on the previous tables and then made the new table with it. And I think one of the reasons, or one of the ways you could implement a data contract there is to have like a true unit test because DBT tests currently are more like quality tests. They're not unit tests. So if you had a unit test where you said this model is actually a function and we have this static input that we're going to pass into the function and we expect this static output, then you could actually say, well, this function meets the contract, this model meets the contract. But we don't. Well, you could do that today. You could build like these static sets, store them in Snowflake somewhere, and then have your result set to compare to as well. You could actually build that in DBT today. It's just not natively supported out of the box.
Yeah.
Right. We actually had Michelle Ark from Shopify present previous Data Quality Meetup exactly that solution. So at Shopify, because they have such an enormous data volumes, they're not using DBT tests on actual data. They use it on synthetic data sets, just like you suggested, David. Yeah. I think we are. Yeah, I think it's actually surprising that we're not really approaching data testing from more like classic software engineering, fixed inputs, fixed outputs, kind of approach, right? I'm also curious, to the extent that data contracts are needed for reliable change management, I'm really curious to hear from Richard and Michael, given that you're working in an organization which is very large in terms of the number of people potentially affected and using data products. How do you approach change management given just the amount of data and complexity of data that's coming in and number of consumers that you have downstream?
Yeah, so I can probably comment one or two things on that. So yes, as you know, like telecom is like just lots of old school stuff, right? All over the place, everywhere. But there's lots of databases like Oracle, even DB2 on mainframe, believe it or not. But there are still modern technologies that can solve this problem. So we use Shrim on a lot of the on-prem existing data sources from Oracle. So those are actually replicated by binary logs using the trail files into BigQuery directly. But there's many different products, right? So I'm not like expert in data contract, but I think in my opinion, it's the easiest thing is to be able to manage those kind of using binary logs to make it automatic for majority of the use cases. Backwards incompatible changes, especially in a large organization from these databases, is extremely unlikely because you have because we actually look at the statistics of those things is extremely unlikely because the amount of things you break because of these kind of changes is so enormous. So that is actually a problem that is a very, very small chance of happening. So it's not almost not worth solving. So, but the majority of the use cases, whether, for all use cases, we use Shrim at the moment, but there's other things like Fivetran, other people, other guys I mentioned about, there's also Google Data Stream that it's quite limited, but it's kind of getting there, right? So, but by utilizing those kind of things with the binary log changes, capturing, it actually handles the schema changes very reliably. All of these things are actually in the form of events. So in the BigQuery concept, they're all getting streaming inserts into rows on top of each other and append only. But these tools often have capabilities to send these as messages into event streams, such as PubSub or Kafka or other things, right? So you actually always have this kind of event driven with the schema is there, right? Because it's relational database where it comes from a lot of these data sources. Whereas for other things, maybe comment on batch sort of things, in my opinion, it really depends on how important that data is to you. So you might think there's lots of them, but actually the ones that's so valuable, that transactional data that you can't break, they're actually usually not that many from my experience I've seen. So I think it's important to prioritize whether you actually can store the data in a semi-structured way. For example, BigQuery has recently announced something called a JSON data type, which you can actually do tree-based lookups to even save your cost on that, which is extremely clever. And then those things like you can, for things that are not extremely important, you can actually get them ingested as JSON data types, which you can actually define a schema afterwards. But for super critical stuff, whether that's batch or real time, you probably want to make sure like transactional data, transactions is specifically or people's orders, you probably don't want to mess around with not having any contracts. But I think that's my opinion. I don't know, Michael, if you have anything to add.
Yeah, no, yeah, I think I share the same sentiment. Yeah.
I think Richard, you brought up an interesting question of knowing the criticality of data. I think that what's interesting is that it's one of the reasons why kind of the ideal data contract seems appealing is in large organizations, you may not know the impact of all the data you build, all the data you have, because people may build dependencies that you necessarily are aware of, unless you have a really good system to actually understand all the usages. I'm just curious how that works in your organization. Like, let's say someone builds a really important application, be that exec-facing dashboard or machine learning, would your team necessarily know about it? Or how does the process work so that you're not basically accidentally become accountable for data that someone is now using for critical applications?
So this is very interesting question because we as a data platform function that we look after we call it kind of data democratization as a buzzword in a sense. So it's basically kind of we have like a core data modeling functions. So there will be things that are experimentation based, like we strictly control, or I wouldn't call it control, like work with other teams. If there's a service account involved on automation, that we're very careful with those areas, and then we share data via kind of like a data mesh way in a centralized area, or in the GCP space, it's like we have a dedicated project called Customer Data Hub. That's where we only have authorized views in BigQuery to share that data. So it's all contract based. There's no exceptions but there are other areas where people are quite free to experiment, including some DBT project if they're on UAT, that's fine, right? But when people start building, downstream systems, I think reporting is probably just one side of the things that, to a degree, may be important. But the more important things are live machine learning models, and also we have so much operational workload, including communication to customer using a lot of this data we have in the first place. So these are very strict defined contract, but we basically created a self-service framework for people to do permission management via Terraform and pull request based. So we have approval groups who know what they're talking about, and then we have Confluence document to do what are the criteria. So you're right, it's very difficult to control, but if you have a platform team that is as evangelist working with the rest of the teams to basically making sure we know what the important ones are. There's no surprise. We never open up data lake. Just there you go. Of course, like that you would end up with lots of problems. But we try to collaborate. What we don't do is we don't try to control everyone to experiment. You can experiment a lot of these things, but as you start building on the production use cases, the tangible stuff, it actually reduces, right? It's not actually that many. It reduces a lot. So that's where we started putting a bit more control in place to make sure the quality of those data sources.
Makes sense. So basically, you can try, but if you really want to put it into production, then you have to go through pretty much like an official request for building, and then you kind of pretty much have a contract this way, which is very interesting.
It's because we're in a regulated business, so we can't just do whatever we like, right? There's lots of things we need to work with other teams, including privacy compliance, to make sure we follow the legal advices and regulator advices. So it's not there's data ethics and all sorts of things. So experimentation is fine in a restricted space where permission is given to those data points. But when we start unlocking, activating data points, is where it's tightly controlled on. Exactly how we can expose those things, because otherwise it's not just about things are broken, you can break the law as well. So it's very important to keep these things into account to protect our customers' data.
Makes perfect sense. I think what's also interesting to explore in that area is to what degree data quality is a problem that the data team ultimately is fully responsible for, because I think that in the current conversation around, well, why are we even talking about data contracts? It's because we have teams who are producing data, and then they are a lot of times not really fully aware of the usage of data, so they're changing things all the time, and then we data practitioners need to clean up the mess, and we are basically we are yelled by stakeholders, and then we are getting blown up by the software teams, and we're kind of like in this really vulnerable position. Do we believe that who is ultimately responsible for instrumenting reliable change management, quality, observability of data? Is it like platform team? Is every data pod is responsible for their own thing? Is it like, are we actually going to have software engineers implement certain quality solutions, or ultimately like who needs to take responsibility for that? Is it like a central thing or more of centralized?
Oh, is that a question for me?
Everyone, but yeah, if you have ideas, Richard, definitely welcome.
Yeah, I just want to give others a bit, but I'll probably just add one thing. So in my opinion, it's more of I definitely think it's decentralized, because otherwise you can't scale as a function, right? So especially in a large organization, it just can't be a centralized team doing everything. So the approach we're adopting is more of it's very key to define ownership of SMEs. So the centralized team, we kind of, what we're trying to do is we kind of allow the individual experts in their area to build, but then if we identify areas that people are duplicating work, and then we start trying to over time pull a little back a bit by bit. So that means we're not actually slowing down everybody, and especially when some of the areas that kind of become independent functions. But one of the key things is, if you're going to build it, you have to own it, right? This is our only, I would say, policy in place. If you want to build it and you don't want to own it, then that's taken away from you. So the power. So if you build it, you own it, right? And then if there's a mess, we're not going to, as a platform team, we're not going to clean it up for you, but we have guidelines. And then we say, okay, if you two are both doing the same thing, because we see everything, right? We are evangelists and helping others to work together. And then we see, oh, these two teams actually not working together. Can we actually, help you to work together? And then we have one centralized data models, and then we bring things in the centralized team that you can work on other things on top of it, right? Then so in this way, you can not only move fast, but also not have a mess down the road. Well, that's from my perspective.
And for me, I think it's a matter of ownership, like Richard says, because I think that when something fails about data, it is just like the data team which is in the light spot, but everyone shares this responsibility to give a good data to the data team. So when we have like a ticket in a software problem and we will end up by the documentation, we should also communicate about the change that we will apply to the data for the data team. And in Doctolib, what we have is that for batch data, for example, we will have a system in data to protect ourselves, to detect the changes that could happen to the database that we are pulling data from. So it is a mutual work with the software team and the data team to detect those changes, and we have a automatic pull request that will change the structure. Then Redshift won't fail at the production, and it is kind of a data contract for batch. And for streaming, we could have another sort, because we could have an API that have data validation. So if the structure is not what we expect, so they have error status, so we can control what we have in streaming. So we handle it like that.
Yeah, at Convoy, we've, as a platform team, have kind of taken the responsibility of developing the tools, but like Richard said, we need to take a decentralized approach to kind of the ownership of these things in order for these processes to scale. So the platform team at Convoy develops the tooling that allows people to ensure data quality, but then in the case of data contracts, the ownership of the end data products, so your ML models, your executive dashboards, those are owned by folks on the data side, on the data team, but the people who are producing data for those kind of critical production path pieces of data, like the data that is generated to train our pricing models at Convoy to know how we price shipments, that is then owned by the software engineers, but the data platform team provides the tooling to make everybody's job easier on that front.
Got it. So basically the importance of the platform team, basically the platform team is the driving force for establishing the guidance for both the kind of applied product facing data teams who are building stuff using data, and then also pushing these guidelines to data producers like software engineers. It sounds like this is a kind of prevalent structure across what you three shared in your organizations.
Yeah, and don't get me wrong, this is really difficult, right? Not like easily to say, but it's extremely difficult to do.
Yeah, absolutely. Cool. we are 3 minutes over our scheduled time. I wanted to thank everyone who joined today for giving a lightning talk and participating in the panel discussion. I think we touched on a lot of the really important thoughts and ideas, and we will do transcripts of all the talks and publish the videos, and you can then reshare and have those so that everyone who couldn't attend today live can also learn from you all. And our next data quality meetup is going to be on December 8th, so in about 2 months, and looking forward to seeing everyone there. Thank you so much again.
Thank you
so much. Thank you.
Thank you.
Thank you.
Thanks.
Bye.
Bye.
Thanks, everyone.